A very good morning to all those present here physically in lecture hall and all those watching later online. My name is Agastya Vishwanath. As you know, I'm a lecturer and professor for these series of lectures on calculus. Once again, these lectures are in association with both the Dancerian Society of Mathematics and Physics and the Y Project. Okay, so in our previous two lectures, we've talked about the concept of what a derivative is, right? And we also looked at how to mathematically calculate one. What is the mathematical infrastructure we use to figure out what derivatives are? And we took derivatives. We figured out how to take the associated limit, right? We figured out how to do differentiation by definition, it's called, right? And we took many derivatives. I even gave you some problems to do, right? And hopefully now we've got a good understanding of how to take the derivative of a function. Now, in this lecture, lecture number 3, we're going to be talking about something called differentiation rules. Now, hopefully you noticed that in the last lecture, not only was I taking very simple functions, but even those simple functions, the algebra required to solve the limit was quite hairy and time consuming. And those were, as I mentioned, very simple functions. When you have more complicated functions, right, or God forbid, compound functions, right, or nested functions, right, when you've got functions like those, then the amount of algebra and time you'd need to do it by definition with that limit would be huge. So, as a consequence of this, for everyday life and for actual practicality, mathematicians have come up with a set of rules which sort of short circuit this process. They make it easier and faster to take derivatives, right? So, it's basically a set of rules which allow us to take derivatives, and these rules are all based on the original definition which I showed you last time. They're all proved with the original definition, but you can use these rules to take derivatives much faster and much more painlessly, right? So, we're going to be learning these rules, and we'll also be learning at the end how to take the derivatives of trigonometric, exponential, and logarithmic functions, right? We'll also be learning that at the end. It's also part of the differentiation rules only. So yeah, that's what we're going to be doing in this lesson. Now, I am going to be showing the proof for each of the rules in the lecture itself. But this lecture, if I went through in detail the proof of each of the rules I'm about to teach you, then this lecture will be huge, right? So most of the one I'm just going to show it to you. Feel free to pause the video, take a screenshot, or just pause the video and go through it at your own pace, whatever you would like to do. If you're present in class, I'll be sharing the proofs with you later on, right? But so please feel free to do that. I may go through some proofs like actually by myself and explain it if I find them extremely interesting or very important. But for most proofs, I'm just going to display them and then move forward, right? Because I don't want this lecture to become too long or too confusing, right? So yeah, proofs are important. I especially value it if you understand the proofs behind the rules that you use, but I won't be going into great detail in this lecture, that's all I'm saying. That being said, let's get into it. So we're going to start off with some very simple rules, right? The first of which is the constant rule, right? That tells me that the derivative of a constant is 0, right? Now, what does the derivative of a constant mean? Derivative of a constant means is that if I've got a function, right, which is a constant, so for example, f of x is equal to 9, well, so what does that function mean? That means no matter what input I put, right, the output will always be 9. So f of 5 is 9, f of 100 is 9, f of minus 50 is 9, right? No matter the input, the output is always the same, 9, right? So for these kind of functions, which are constants, but this rule is saying that if I take the derivative of this, I get 0. Now, initially this might seem a bit weird, right? Like why? But the more you think about it, the more sense it makes, right? What is a derivative? It's a measure of the rate of change, right? But these functions are just constants, they don't change, right? It's 9 throughout, it's just a flat line if you were to graph it, right? So the derivative at all points will be 0. It's not changing, so there is no rate of change. If you want to think about this as a car parked in a garage, as I said, right, the distance a car travels can be considered the function and the speed can be considered the derivative, right? So if the car is not moving, if the distance is always the same, right, then the speed will be 0, right? So a car in parking lot has no speed. That's just another way to think about it, right? But hopefully it's fairly obvious that if you've got a constant which is not changing, right, its derivative is just 0. So like the derivative of 5 is 0. Derivative of 107 is 0. It doesn't matter what the constant is. Derivative of minus 9 is 0, right? And all these are, of course, functions, right? We're considering them to be functions. Okay, so that's just a constant rule, right? Fairly simple. There is technically like a proof by definition for this, but hopefully I've explained it intuitively enough where you don't need to see that. Alright, rule number 2, the x rule, right? Now the x rule is fairly simple. It just says that the derivative of x is 1, right? What does this mean? It just means that if f of x is equal to x, right, that function, right, the derivative of that function is 1. That's all it's saying. So f of x is equal to x means that no matter what the input is, the output will just be that, right? So if x is 2, then the output is 2. If x is 5, then the output of the function is 5, right? So f of 5 is 5, f of 6 is 6, so on and so forth, right? So we're saying the derivative of that function is just 1, right? And hope this also might seem a bit weird at first, but hopefully it makes immediate sense, right? The derivative, the rate of change is just measuring how much per unit increase in x the function changes, right? So if the function is equal to the input, then if you increase x by 1, f of x also increases by 1. So the rate of change is just 1, right? If you want another way to think about it, if we graph the function y is equal to x, right, and we look at its gradient, its slope, which is its rate of change, its derivative, right, that's also 1. So it's commonly known fact that the y is equal to x line has a slope of 1. So you can hence say that its derivative is also 1. These are just different ways to think about it. Once again, do not get too attached to the idea of a graph. It's just a way for us to visualize and confirm things. So yeah, there's no need for examples for that one. Like this is just the one. D by dx is equal to d by dx of x is equal to 1. Right? That's what we need to remember. Okay, those are the two very simple rules. The next ones are also fairly simple, but this is good to go through them, right? So the coefficient rule is the next one, rule number 3, right? And that just says this: if we've got the derivative of a constant into another function, that will just be the derivative of the constant, the constant into the derivative of the function, right? Now what I mean by this is if you're taking the derivative of the function, which itself can be written as a constant into another function, right? Let's say c into f of x, and that will just be c in the derivative of that whole function will just be c into the derivative of f of x, right? Basically, you can take constants out of a derivative is another way to think about it. This might be a bit difficult to think about it the first time, but let's look at some examples, hopefully it'll become clearer. So let's say I've got derivative of 5x, right? Now we know the derivative of x is 1. So what I can say is I can write this as, according to this, x is just a function, right? So I can say this is the 5 into the derivative of x, right? Just applying the rule, right? I can take the constant out. What is the derivative of x? It's 1. Just we just learned that, right? So I can just say it's 5 into 1, which is just 5, right? So we can just take the constant out of the derivative, right? Let's have a look at another example. In the last lesson, we learned the derivative of x squared is 2x. So we've got 7x squared, right? So I'm going to take 7 out. It's just 7 into the derivative of x squared. Once again, just applying the rule here. And we get 7 into 2x, which is going to be 14x, right? The proof for this is fairly obvious, right? So I'm not going to show it here either. Please just, in fact, this is very simple. You can probably prove this yourself, right? So if you're watching online, it's a good exercise. Pause the video and just write down limit that's equal to 0 of c into f of x plus h minus c into f of x over h, right? And you'll immediately figure out how to prove this rule, right? So it's not really worth showing the proof. People who are here physically, just you can do that at home, or if you have time, you can do it right now. Okay. And of course, yeah, there's one more example we have here. So 9 into root x. We can take the constant out, 9 into the derivative of root x. The derivative of root x, as we learned last lesson, is 1 upon 2 root x. So we get 9 into 1 upon 2 root x, or 9 over 2 root x, right? So this basically makes my life a lot easier. Earlier, I would have to plug this into the full limit and take it again. But this, I can just take out the constant, and even if I don't know what this derivative is, it's just easier to take this instead of this plus the constant, right? So yeah, this just makes a life a lot easier. And you'll see this constant theme throughout all the rest of the rules. Okay, now we get to some more interesting rules, but still fairly simple rules. The sum rule. Now, if I got the derivative of f of x plus g of x, right? So some function plus another function, if I want to take the derivative of that entire thing, right? That is just going to be equal to the derivative of f of x plus the derivative of g of x, right? This may seem obvious, but this is in no way obvious, right? Like I'm basically saying the derivative of the sum of two functions is the sum of its derivatives, right? That's what this rule is saying, right? And this does have a proper proof, which I will show you at the end, but let's first get an understanding of what this is actually trying to say. So if I've got two functions added together, let's say 3x plus 5, right? Normally I would have to go put this into my limit and do all the math, but instead of doing that, I can just split it and say this is going to be equal to the derivative of 3x plus the derivative of 5, right? And these two to differentiate individually are quite easy. So derivative of 3x, as you learned, is just I take the 3 out, derivative of x, so it's going to be 3, right? Now derivative of 5, and if 5 is a constant, this is going to be 0. So we get 3. 3 plus 0 is 3, right? Great. 7x squared plus 9x, great. Now what we've got to take, once again, we can split the derivative into derivative of 7x squared plus the derivative of 9x. Right, now for derivative of 7x squared, first I take 7 out, becomes 7 into derivative of x squared. Derivative of x squared is just 2x, so 7 into 2x, 14x. Derivative of 9x is 9 into derivative of x, we take 9 out, which is just 1, so 9 into 1, 9. And this have to add them, and that's my derivative. Easy as that. Final one, derivative of 2 root x plus 5x squared, right? Now imagine taking the derivative of this, the derivative of this with like the limit, right? That would be kind of painful, actually very painful if you think about it. But with the sum rule, it makes our lives a lot easier. If we take this just becomes the derivative of 2 root x plus the derivative of 5x squared, right? What is the derivative of 2 root x? I can take 2 out, 2 into the derivative of root x. The derivative of root x is 1 over 2 root x, as we learned last lesson. This becomes, so 2 into 1 over 2 root x just becomes 1 over root x. Now, derivative of 5x squared, I take 5 out. We get 5 into derivative of x squared, which is going to be 5 into 2x, so 10x. 1 over root x plus 10x. That's all there is to it. And see, easy as that. It's not too difficult, and this, especially in the case of this last one, it makes our lives a lot easier. Okay, great. And you can also see how I've been applying the coefficient rule throughout this, and it's also made my life easier. So you can see how these rules allow us to take derivatives much faster. Right? Like I could glance at this and tell you what the derivative is. Whereas if I had to do it by actually working out the limit, that's going to be much harder. Okay. Now this is the proof, right? It's just fairly simple algebra. You take f of x by g of x, you bring the f of x terms on one side, and then you split it, and you can split the limit as well. And this is just going to be the derivative of f of x, this is just going to be the derivative of g of x. So you can quite easily show that the derivative of f of x plus g of x is just the sum of the derivatives, right? This is just the proof. Please, if you are more interested, pause here or take notes if you're in class and have a look. Okay, great. Next rule, the difference rule, or the subtraction rule is sometimes called. It's literally the same thing as the sum rule, just for subtraction, right? Yeah, I don't think anything needs much explanation. So let's just jump straight into the examples. What is the derivative of 4x minus 7? But once again, this is the derivative of 4x minus the derivative of 7. So for the derivative of 4x, we take 4 out. The derivative of x is just 1, so this just becomes 4. 7 is a constant, so the derivative of a constant is 0. We get 0. 4 minus 0. Oh, 4. Sorry. I clearly was probably thinking about something else and making this stupid. Yeah, that is 4. I apologize. That's supposed to be 4. Great. Okay, next one. Derivative is of 2x minus 3x squared. Right? So once again, we can split the derivative. We get the derivative of 2x minus the derivative of 3x squared. We take 2 out. 2 into the derivative of x is going to be 2, and we get now. So we put that there. Now for the second derivative, we get the derivative of 3x squared. Take 3 out. Derivative of x squared is 2x. So 3 into 2x, 6x. So we get 2 minus 6x. Not too difficult. Great. Now this one, once again, imagine if you had to do this by definition. It would be a nightmare, right? Now see how easy the differential makes it. Let's do derivative of 5x squared plus the derivative of x, root x, right? So the derivative of 5x squared, we take 5 out and multiply by 2x to get 10x. And derivative of root x, we know is just 1 over 2 root x. So we get 10x minus 1 over 2 root x, and we're done, right? Now the proof for the difference rule is literally the exact same thing as the proof for the sum rule, right? Or you can just prove it using the sum rule and the coefficient rule. Like it's just quite simple, so I won't be showing it here. Okay, the power rule. Now here is where we start to get a bit more interesting, right? So at this point, if you're feeling slightly uncomfortable with the idea of differentiation rules, please feel free to pause or rewind the video to get a better understanding of them, because here the rules start to get a bit more interesting and a little bit more complicated, but also more useful. Okay, the power rule. Now this allows us to take the derivative of a function x to the power n, x squared, x cubed, anything, even fractional negative powers, but we'll get to that later, right? So it allows us to take this derivative. Quite interesting, right? Quite useful. And it turns out that if you want to take the derivative of x to the power n, that's just going to be equal to n into x to the power n minus 1, right? So we multiply x by n and we reduce its power by 1. You can sort of think about it bringing n down and subtracting 1, right? So d by dx of x to the power n is nx to the power n minus 1. Pretty useful to know. Very useful to know, actually. So let's look at some examples. Let's go back to our old friend, the derivative of x. Let's try derivative of x cubed first, right? So once again, to take the derivative, I need to multiply x by 3, and then I need to reduce the power by 1. So I get 3x squared, right? Let's try another one, derivative of x to the power 5. I need to, we can sort of think about it as bringing 5 down and reduce it by 1. We get 5x to the power 4, right? So it's quite simple, and the more you practice this rule, the easier you'll find it to apply, right? And let's go back to our old friend, the derivative of x squared. So we can bring 2 down, and we just need to subtract the power by 1. So 2 minus 1 is just 1. We just get 2x. Wonderful. And this is an easy way, once again, to show that the derivative of x squared is just 2x, right? So all we're doing is we're taking the power down and we're reducing it by 1. we're just multiplying it by the power and reducing the power by 1, right? Now this, we've been using whole number powers, but this actually, interestingly enough, works for negative and fractional powers as well. You'll see why. So let's also try one more. Derivative of x to the power 9 is going to be 9x to the power 8. Let's try a really big one. We can bring it down and reduce it by 1. This works no matter how big the power is, right? So we bring 100 down and reduce it by 1, 99. 100x to the power 99. Perfect. As I was saying, let's check out how this applies for negative and fractional powers. Okay? So now we've got 1 over x. Now you might think, how does the power rule have anything to do here? Well, I can write 1 over x as x to the power negative 1. And this is just x to the power n, right? So the power rule actually does work for negative powers, as I said. So you can simply bring negative 1 down, so you get negative x. And now negative 1 minus 1, that's not going to be 0, it's going to be negative 2. So we get negative x to the power negative 2, just applying power rule. That's just going to be negative 1 over x squared. And that's exactly what we got for 1 over x when we differentiated it by definition in the last lecture. So it is indeed correct. And it makes it much easier, right? Like it makes it much easier to take that derivative as compared to what we had to do by definition last lecture. Okay, now 1 over x to the power 9. Now if you have to differentiate this by definition, good luck, right? You have to expand x plus h to the power 9. But no, you don't have to do that in this case. You can just write it as x to the power negative 9. You get negative 9 x to the power negative 10. So negative 9 over x to the power 10. As simple as that. Perfect. Power rule makes our lives, particularly the power rule, like it's invariably useful. Okay, great. Let's move on to root x. Now you might think, root x? What does root x have to do with the power rule? Well, as you might remember, we can write root x as x to the power 1 half. And the power rule also works for fractional powers. So we can bring half down, so we get half x to the power 1 minus half is going to be negative half, right? So we get half x to the power negative half, which is rewritten 1 over 2 root x. So yeah, and we know this is the case. So once again, further validating the idea that the power rule can be used in this case. Let's try fourth root of x. This would have been a pain. This would have been very difficult to do by definition, but we can now just simply write this as x to the power 1 over 4. So 1 over 4 into x to the power, we got to do 1 minus 1 over 4 minus 1. That's going to be negative 3 over 4. So we get negative 3 over 4. So 1 over 4, 4th root of x cubed. That's one way to write x to the power 3 over 4. We're great. And we're done. So we can use the power rule even in these circumstances. It's a very versatile tool in our toolkit. Now if you're wondering what the proof is, it's just this. It involves the binomial expansion theorem, right? And basically it hinges around the fact that when you expand x to the power h to the power n, x plus h to the power n in general, right? You get this series, right? And x to the power n and minus x to the power n will always cancel. And you have basically nx to the power n minus 1 will always be the first term multiplied by h. And you have all these other terms. You can then take h common, right? And this is the only term without h, and all these other terms will eventually have h. So you can see we do that here. And then when we take the limit as h approaches 0, we just substitute h is equal to 0. And all these terms disappear, and we're just left with the first one. That was I explained that very fast, but as I said, that's not the focus of this lesson. So in case you are really interested in the proof for this miraculous rule, the power rule, please pause the video and have at it. Okay, let's move on. The product rule. Okay, things are getting very interesting and also very complicated. So this one is slightly complicated and difficult to remember, but it's very useful. So let's jump to it. So the derivative of f of x into g of x. So as the name probably indicates, we're taking the derivative of a function multiplied by another function, right? You could think of this as maybe x squared multiplied by sine of x, or tan of x multiplied by cos of x, or root x multiplied by x, right? We've got one function multiplied by another function, right? How do I take this derivative? Well, it actually is funnily enough, the derivative of the first function into the second function plus the first function into the derivative of the second function. Some people like to write it the other way around. It's addition, so it's transitive, right? We can also rewrite it as the first function into the derivative of the second function plus the derivative of the first function into the second function. Like they're the equivalent, right? Just switching the terms around. Some people like to write it like this. Some people like to write it like this. It's up to you, right? Now, this is very difficult to remember, so don't worry. And I'm not sure if I said this at the beginning, but this is a very content-heavy lecture, right? It is going to be, and it continues to be, a very content-heavy lecture. So don't worry if you understand everything at first. Don't worry if you've got to rewind the lecture a few times, rewatch it, it's fine. Don't worry if you don't memorize this on site. Feel free to note it down and use it again, or I'll mention this whenever I'm using it, right? So don't worry, right? I'm not expecting you to pick up all this knowledge immediately. This is a very content-heavy lecture as compared to my previous ones, right? But yeah, So this is a very useful tool, but slightly difficult to remember. But trust me, the more you use it, the more you'll remember it. Like I've got locked down solely because of the fact that I use it so much. Now for the second version right here, there's actually a acronym of sorts you can use, not even an acronym, just something to remember it by. This is invented by 3 Blue 1 Brown, Grant Hardison. Please check him out in case you're interested. So it's right d left and left d right. Right d left plus left d right. And of course, d in this case represents the derivative, right? That's for the second version. And you can use first, second, whatever suits you. I tend to prefer to use the first. Okay? Now let's see this power product rule in action. What can it really do? How does it help us? And hopefully when we apply the rule, it will get a bit more easy to understand. So let's say you've got x into root x. Now I could technically use the power rule here, right? Just writing this as x to the power 1.5, but I won't do that. I'm going to just use the product rule just to get a good understanding, right? Because we don't know the derivative of that many functions yet, like sine of x and cos of x and e to the power x and functions like this, right? I'm stuck using just polynomials for now. Okay, so using the product rule to differentiate this, we're going to take the derivative of the first function, so d by dx of x. We're going to multiply it by the second function, square root of x, right? Now you're going to add just the first function, x, and we're going to multiply it by the derivative of the second function, d by dx of root x. Now, the derivative of x is just 1, so we get this first time this becomes root x, right? Now x into the derivative of square root of x. So the derivative of square root of x, 1 over 2 root x. So x into that will just be x over 2 root x, right? You could probably simplify this a bit further, but I'm just going to leave it as it is. Great. So that's really all that there is to it. You could add these two terms together. It's not too difficult, but I'm going to leave it as it is for now. Okay. Now here's another one, right? We've got 7x to the power 9 plus 3 over x, right? Now you might think, how do I use the product rule here? Well, divided by x can also be written as into 1 over x, right? So now we've got, hopefully now it's clear, we've got two different functions, right? 7x to the power 9 plus 3 into 1 over x. Now here you have to use the product rule. There's no alternate way to do this, right? Now, how do I do this? Well, same thing, same logic. We're going to take the derivative of the first function, multiply by the second function, then just the first function, multiply by the derivative of the second. Now, what's the derivative of 7x to the power 9 plus 3? Well, this is two functions added together. So I'm going to differentiate them individually and then add it. So we get 7 out, so x to the power 9 you just learned is going to be 9x to the power 8. And bring the 7 back in, so we get 63 into x to the power 8, right? And plus the derivative of 3 is just 0. So it's just going to be, this is going to be 63 to the power 8. You can see that right here. Now 1 over x remains 1 over x, this remains this. Now what is the derivative of 1 over x? This is negative 1 over x squared, right? So you can write that there. Then we just multiply out and we get this perfect little expression. And we needed to use the product rule here. There was no other way to do this. This was probably simpler to use the power rule. This one needed the product rule, okay? And as we learn some more functions like sine, cos, logarithmic functions like ln, when you learn those derivatives in this lecture itself, you'll see that the product rule becomes more and more useful. Okay, this is the proof for the product rule. By the way, I should probably mention that I have not written these proofs. I've taken them from the internet, but the proofs are just universal mathematical knowledge, right? This is fairly simple. Like, it's not actually, no, it's not very simple. Sorry, it's quite complicated. But basically, what you're doing is you're isolating it in terms of f of x and g of x. So you can take g of x common and g of x plus h common to get a derivative here, and f of x common to get the derivative here. And you do that, and you get at the end f prime of x g of x plus f of x g prime of x. That was not a very good explanation, but I'm trying to move forward, right? So if you are actually interested in this, please pause the video here and go through this proof. It's quite interesting actually, but I'm not going to go spend too much more time explaining it. Great. Okay. Now the quotient rule. Okay, this one you have no hopes of remembering on your first try, but don't worry, I'll be mentioning each time I use it, and it's like probably the biggest rule we're going to be introducing today. Okay, it's like the boss. Okay, like the in a video game you reach the boss fight. Like this is the boss of the differentiation rules. It's the one that trumps all. Maybe the chain rule might be a big one, but this one's quite big. So now if I got the derivative, as the name indicates, of the quotient, right? So we've got f of x over g of x, right? We've got a function divided by another function, right? We can always write this as f of x into 1 over g of x, but often it's easier just to differentiate it like this, right? We need to use the quotient rule. And we need to use that. Yes, it's quite something, right? It's substantial. So we've got something similar to the product rule up here, except there's a minus sign. So f prime of x into g of x minus minus f of x into g prime of x. But we need to divide that all by g of x whole squared, right? So that huge, but it's pretty difficult to remember on your first try, right? This is, so the way I used to remember it is, this is quite similar to the product rule, just with a minus, and 1 over g of x whole square is not too difficult. Now, you can differentiate f of x over g of x as f of x into 1 over g of x and use the product rule, but often it will be more convenient, despite how big this is, to just use this, right? Okay, so let's look at some examples. We've got x squared plus 1 over x plus 1. This is there's no simple way to simplify this. You would have to use the quotient rule. So you do that. So you go ahead. This is the quotient rule right here. So you need to write the derivative of the first function. So we've got to take the derivative of x squared plus 1. So I take the derivative individually. X squared is just 2x plus derivative of 1 is 0. So we get 2x only. Just into the second function. Then we've got the first function into the derivative of the second. So I need to take the derivative individually. So this will be derivative of x is 1. Derivative of 1 is 0. So just get 1 plus 0, 1. And over the second function whole square. That's our thing. We just multiply out here and we get this. This simplifies to this, right? Great. Okay, next one. Oh, kind of got cut off here. Sorry about that. But now we've got x cubed plus x squared over x to the power 5 minus 9. Getting kind of complicated now, but we should still be able to do it. Once again, here's the quotient rule for reference. Now take the derivative of this. We're just going to take the derivatives individually. So we get, bring the power down and subtract 1. So 3x squared. And then this is just 2x. So 3x squared plus 2x. We multiply it by the second function. Then we just write down the first function. And now for the derivative of this, I'm going to take the derivatives individually. Bring down the 5. We get 5x to the power 4 minus 9. Now, so the derivative of 9 is just 0. So we get 5x to the power 4. And we divide by the second function whole square. This is a pain to expand, but you can do it, and eventually you get that. Great. Okay. This is the proof of the quotient rule by definition. It's quite substantial, as you see. I'm not going to go through it, but it's in fact easier to prove the quotient rule using the product rule and the rule we're about to cover next, the chain rule. So I would not recommend using this. Instead, prove the product rule and then use the chain rule to prove the quotient rule. You'll see what I'm talking about in a moment. And by the way, it's quite important that I mention that at this point, you may not understand everything immediately. You may find that I'm going really fast, but yeah, this is going to be a very content, as I said, it's going to be a very content heavy lecture. It's okay if like you're not immediately like as good as I am while taking derivatives, so you're not doing it as fast as I'm doing it. As long as you're understanding the fundamental concept, even if very slowly, that's all that's required, right? So even if you feel like I'm going really fast, that's just because I need to get through a lot of content in the lecture. But don't worry, you can please rewatch this lecture as many times as you need to and go as slow as you need to while taking the derivatives. I just do them fairly fast for the interest of time, right? And yeah, and I'll be sharing problems at the end for your practice, so don't worry about that. Okay, now the chain rule. This is the chain rule right here, right? This is a Leibniz notation, I'll get to that, but this is the chain rule. So the chain rule is when you've got composite functions, nested functions is another thing to call them. When you've got f of g of x, this could be sine of x squared, for example. I've got one function and another function inside that function. Or maybe square root of 9x cubed. So 9x cubed is the inner function and I'm taking the square root of that, right? These are called composite functions. And their derivative, it's kind of funky, right? Like it's not difficult, it's just kind of weird. So we've got to take the derivative of f of x, right? It's outer function, but in terms of g of x. So we're going to input g of x. For example, if I've got the derivative of x, if my outer function is x squared, right? Like I've got sine of x squared, right? Let's say I've got sine of x whole squared, right? Then the outer function is x squared. So I'm going to take its derivative, which will be 2x, but instead of putting x, I'm going to put g of x. So it become 2 sine of x. So sine of x whole squared, take the derivative, becomes 2 into sine of x, right? We put the input as g of x, not x, right? It's a little bit difficult to think about, but trust me, as you do some examples, you'll soon become clear what I'm talking about. But we're not done, right? We need to then multiply by just the derivative of this inner function, g prime of x, right? And once again, this may seem a bit wishy-washy or hand to be at first, but don't worry, as we do examples, it'll hopefully become incredibly clear. Oh, I do want to mention one thing, is when we write this in Leibniz notation, it's kind of weird. Like that's a theme with the chain rule. It's a little bit weird. So when we want to write this in Leibniz notation, how do we write f prime of g of x, right? Well, we write d by dg of f of g of x, right? And you might wonder why, but so remember when I say the derivative of f of x with respect to x, right? So when I want to take the derivative of f of x with respect to x, that is df dx, right? I'm taking a teeny tiny change in f and dividing it by a teeny tiny change in x. But this is a derivative with respect to g of x. So I'm taking a teeny tiny change in f of g of x and dividing that by a teeny tiny change in g of x, right? That's what this is. This is just equal to that, right? But we're taking a derivative with respect to g. So this is how you write this in Leibniz notation. If you're still kind of confused, I don't blame you. Right? Here's another way to think about it. Let's just call g of x some other thing a, some other variable a. So g of x is equal to a, right? So now this just becomes d by dA of f of a. So what is d by dA of f of a? This is going to be f prime of a, right? Just the derivative of f of x, of the derivative of f with respect to a, f prime of a. And if you remember, a was just g of x, so we get f prime of g of x, right? There are some ways to conceptualize it, but the reason I want to introduce is just because this is how we write this in Leibniz notation. Might be a bit confusing at first, but I'm sure you'll get it the more you use it. And of course, g prime of x is just dg dx. dg by dx, yeah. Okay, great. Now let's apply this rule. Let's say you've got square root of 7x cubed, right? You could solve this using the power rule by taking root 7 into square root of x cubed, right? But often it's actually, in fact, in this case, it's a little bit easier to use the chain rule. So how? Well, first what we've got to do is we've got to take the derivative of the outermost function. What is the outermost function? Square root x. So what is the derivative of root x? 1 over 2 root x. So I'm going to write down 1 over 2 root, but instead of putting x, I'm going to put the inner function, right? 7x cubed. So the square root of 7x cubed, I'm going to take its derivative 1 over 2 root x, but I'm going to do 1 over 2 root 7x cubed. Instead of x, I'm putting 7x cubed. And we're going to multiply by the derivative of the inner function, 21x squared, right? That's, you just use the power rule for that. You take 7 out, you bring 3 down, so you get 21 and then reduce power by 1 squared. And thus it becomes 21x squared over 22 square root of 7x cubed. Great, right? You could have also solved this using the power rule, but whatever. Okay, next. Now let's see, we've got 1 upon x squared plus 5, right? You might think, well, the quotient rule is what we used here. But once again, the chain rule is going to be much faster, right? How so? That we can write 1 upon as to the power minus 1. So this just becomes x squared plus 5 to the power minus 1, right? Now what is the derivative of 1 upon x? Negative 1 upon x squared, right? So I'm going to write negative 1 upon x plus x squared plus 5 squared. Remember, this is my input. This has got to be my input, right? And now we've got to multiply by the derivative of the inner function. Just we're going to take the derivatives individually. We get 2x plus 0, right? So into 2x. So you get negative 2x over, and we just expand this out, you get that. And perfect. And done, right? And you can see that's much more painless as compared to using the quotient rule. If you had to use the quotient rule for this, it would be pretty hairy. Just because it's 1 upon, we can just write it as negative 1 to the power negative 1, right? Great. Now let's try this one. This is a bit more complicated, right? But we should still be able to manage. So we need to take the derivative of the cube root of 2x plus 1. How do we do this? Well, we can just write the cube root as to the power 1 upon 3. So 1 over 3, we can just use the power rule. We bring the power down and we subtract 1 from the power. So 1 minus 1 over 3 is just, 1 over 3 minus 1 is negative 2 over 3. But once again, the input needs to be the inner function. So we get 1 upon 3 into 2x plus 1 to the power negative 2 over 3. We need to multiply by the derivative of the inner function. So derivative of 2x is just going to be 2 into the derivative of x, which is going to be 2 plus 0, right? So we get 2 over 3 into cube root of 2x plus 1 whole squared. I don't think that's coming in the screen, but it's there, whole squared. That's just a way of writing to the power 2 over 3. Okay, that's the chain rule, right? It can get a bit messy at times, but hopefully it's quite clear. And as we learn some more functions like sine, cos, logarithmic, and so on and so forth, hopefully this becomes slightly clearer. Now, as for the proof, that's actually more pixelated. I'm sorry about the pixelation, but yes, it's a very simple proof. Basically, you have to, the Leibniz notation comes in handy here, right? So you multiply by gx plus h minus dx over g of x plus h minus dx, right? You just multiply both numerator and denominator by that. You take g of x here, put h there, which is multiplication fraction, so it's fine, right? And now what you notice here, we've got a tiny change in g of x in the denominator and a tiny change in f of g of x in the numerator. So this is exactly what I was talking about. D f of g of x over dg, right? This is f prime of g of x. Right? If that's still not clear, that may need some cementing, but just take my word for it in that case, right? And of course, this is just the derivative of g of x. So we get f prime of x, f prime of the derivative of g, f prime of g of x, right? Into g prime of x. That's it. Perfect. Okay. Now we come to trigonometric functions, right? Now, how to differentiate trigonometric functions, right? You might have been wondering about this from day one. And I mean, it's on the board, but like, let's get into the meat of it. So, the derivative of sine of x. What is the derivative of sine of x? Interestingly enough, it's cos of x, right? Why? There's a proof for that which I'll show you, but sort of intuitively you can think about it that initially sort of the slope of sine of x, if you look at the graph, is kind of 1, then at x is equal to, when at pi over 2 it sort of becomes 0, then at pi it becomes like -1, and like that. And you'll see that those kind of values match up with what a cosine curve looks like. So I actually encourage you to draw both curves in your notebook or on your screen or whatever, right, and see how that actually kind of makes sense. Of course, it's a mathematical proof which I'll be showing you later, right? But it's best to just memorize this stuff, it's not too much. Let me call it the derivative of cos of x. Now, if the derivative of cos of x was sine of x, I think pretty great, but it's not. It's pretty close. It's negative sine of x. And once again, if you look at the cos curve and the negative sine of x curve, it'll make sense, right? Okay, fine. Then the derivative of tan of x is secant square x, right? And these are just alternate forms of writing secant square x. You can write 1 upon cos squared x and 1 plus tan squared x. Now, here's an exercise for you to do right now. Pause the video and try. Tan of x can be written as sine of x over cos of x, right? So let's try to use the quotient. I told you what the derivative of sine of x and cos of x are. Use the quotient rule to differentiate it and figure out what it is equal to. Figure out that it proves that it's equal to secant square x or any one of its equivalents. I'll be sharing the solution later in this lecture, but please, if you're in the lecture hall, get to it. And if you're watching online, please pause the video and go ahead. Okay. Let's have a look at the proofs, right? Let's go kind of off the screen. I won't be going into too much detail, just in case you're interested, here the proof for sine of x and cos of x, right? In the interest of time, I am going to gloss over this, right? But it's just, you can use a trigonometric identity to split up x plus, they've used delta x instead of h, right? That's fine, right? It's the same thing, it's just a variable. And then you can use some simple limit identities for trigonometry to figure out this is cos of x and that this is negative sine of x. Now, this is the proof using the quotient rule I was talking about, right? So, sine of x over cos of x, just apply the quotient rule, we get cos squared x plus sine squared x over cos squared x. You'll notice that this is just equal to 1 according to Pythagorean identity, and we can just do 1 over cos squared x, which is secant squared x, right? You could also just take this, split this into cos squared x over cos squared x plus sine squared x over cos squared x, which is 1 plus tan squared x. All analogous ways of solving it, right? Great. So this is how we've got sine of x and cos of x and tan of x derivatives, which are quite useful, trust me, especially when you want to study physics. But now let's move on to the next one, which is exponential functions. So we've been dealing primarily with polynomials. Now we added some radicals and 1 upon x to the power 9, these kind of things to our tool belt. Then we added just now the trigonometric functions. Now we've got exponential functions. So the derivative of an exponential function a to the power x, right? That's just an exponential function, will just be a to the power x into ln of a, right? So this is quite interesting. The exponential function's derivative is proportional to itself, right? It's just off, and in fact nearly equal to itself. It's just offset by this ln of a, right? So we've got a to the power, the derivative of a to the power x is just a to the power x into ln of a. It kind of makes sense when we use these kind of things for population growth models, is that the rate of growth of the function is just proportional to the value of the function at that point in time. So the more people you have, the faster the population will grow, right? That's why that kind of makes sense now when you look at the derivative. As to why this is, we'll be getting into that in a second. Now, we can see that the derivative of 2 to the power x in this way will just simply be 2 to the power x into ln of 2. ln of 2 is just a constant, right? The derivative of 5 to the power x will just be 5 to the power x into ln of 5. Now, here's the question. ln of what is 1? ln of what is 1, right? So, ln of something must be 1, right? Now, whatever that is, think about what that base, let's use that as, let's call that a, right? So, if ln of a is 1, then the derivative of a to the x just becomes a to the x. It's itself. The derivative is equal to itself. So, is there any number such that ln of that number is 1? There is. And that number is e. Oh, sorry. bad timing. I forgot to put 1 there. But my point is, this also works for decimals. So, 3.5 to the power x is also equal to 3.5 to the power x into ln of 3.5. But this was I made the point, right? God, I really messed up that dramatic timing. But yeah. So the derivative of e to the power x is just e to the power x. Why? Because ln of e is 1, right? And this is a really interesting fact. In fact, many people try to define e in this way. Like, this is a valid definition for what e is. It's the constant such that when you raise it to the power x and differentiate it, you get the same function back, right? This is actually a very, very useful property of E, and it's why E shows up in many places in nature, like in physics. Like, in the time it takes for current to circulate through an inductive circuit, like that is, I would not say that was related to E at all, right? But E pops up in them, right? So the reason E pops up in everywhere in physics and everywhere in maths usually tends to be because of this property. Okay, well, that's just an interesting tidbit for you. Now, why is this the case? Why is this the case? Well, that's a little bit nuanced. I won't be going too much into that, but I'll just give you a simple one here. Okay, so if you got a to the power x, this could be equal to the limit of h approaches 0 of a to the power x plus h minus a to the power x over h, just applying the definition. And you notice I can split this into a to the power x into a to the power h, right? I can just take a to the power x whole common, and I get a to the power x minus 1 over h. Now, it turns out that this limit as h approaches 0 tends towards ln of a, right? You can look this up. This limit is a well-known limit, and it tends towards ln of a. So I can just write this entire thing as an a to the power x limit as h approaches 0. It's just a to the power x. H is not involved, right? We just get a to the power x into, as I said, this tends towards ln of a, right? This is not a very satisfying proof because I'm sort of asking you to take me at my word for this, but just trust me on that, okay? Great. Now, the last one we're going to be covering today, logarithmic functions, right? And this is basically, log base 2 of x, ln of x, whatever, right? And we're going to start off with ln of x, right? So, what is the derivative of ln of x? Well, interestingly enough, it is 1 over x, right? The derivative of ln of x is 1 over x. Why you'll be getting that in a bit, but yeah, the derivative of ln of x is 1 over x. Take it from my word for now, right? Now, what's interesting about this, right? What's interesting about it is that if I want to take the derivative of log base a of x, any log, right? I can just use the base change formula to get it in terms of ln. So log base a of x becomes d by dx of ln of x divided by ln of a. Now ln of a is just a constant, so I can take 1 upon ln of a out of the derivative. So we get 1 upon ln of a into derivative of ln of x, which you just know is 1 over x. So we figure out this is just equal to 1 over ln of a into x. And that's indeed true. The same logic I showed you, right? So derivative of log base a of x, any log, would be 1 over ln of a into x, right? Let's have a look at an example. So derivative of log base 2 of x is equal to 1 over ln of 2 into x. Ln of 2 is just a constant. Log base 7 of x, same logic, same everything, right? Now, why is the derivative of ln of x equal to 1 over x? There are many different proofs. This is a particular one which, like, I discovered by myself and I prefer the most. So actually, this is kind of involving a little bit of differential algebra, but I think we'll be fine. So let's say e to the power x is equal to some variable a, okay? So let me take, I know that ln of a is equal to x, right? So ln of e to the power x is just x, right? So ln of a is equal to x. Now I'm going to differentiate, now these are both functions, right? Whatever, these are both functions. Remember, a is a function of x, it's not a constant, right? It's e to the x. So I can differentiate both sides of this equation. Can I do that? Yes, because if these two functions are equal, then the derivative should also be equal. So I'm going to take the derivative of both of these functions, then the equality remains because if the functions are equal, the derivative should be equal. A little bit of differential algebra, but we should be fine, right? Now, what is the derivative of ln of a? Remember, a is not a constant in this case, a is e to the x. So we have to use the chain rule. We get d by dA of ln of a. We don't know what that is yet. We're trying to prove what it is, right? But remember, this is a chain rule. We're taking x, so we've got to multiply it by the derivative of the dA dx. But remember, a is e to the x, so the derivative of e to the x is just e to the x, which is just a. That's kind of confusing, so just pause the video here if you need to just soak it in. And of course, the derivative of x, as we know, is just 1. So now I get d by d of ln of a is just equal to 1 over a. And that's the same thing, and in this case it's a. But my point is, it's been proved that the derivative of ln of x is just 1 over x. I use a here, but it could be any variable, right? This is a proof for that. It's kind of, I know it must be very difficult to understand at this stage, but it's, the more you think about it, the more it will make sense, I promise, right? And you don't have to, if you don't want to, you don't have to concern yourself with proofs too much at this stage. So it's always healthy to do so. And at every stage, it's always good to know the proofs behind the rules you use. Okay. And with that, this fairly long lecture is over, right? It's very content heavy, so don't worry. I'm saying this third time. It's fine if you don't understand everything I've taught, right? Just rewatch this lecture as many times as you need to, take as many notes as you need to, and I'm sure you'll be able to get the concept. Because it's a lecture, my hands are kind of tied. I'm not able to go as slowly as I would like to, right? Or as, like, getting feedback from you guys as I would, people watching online and people present here as I would want to, but it's honestly fine, right? Hopefully this kind of a format didn't bother you too much, and once again, just rewatch it and pause it and do as much as you need to do with this lecture to help that concept just get cemented. That being said, I'm not going to leave you empty-handed. I am going to give you some problems, practice problems. So you should be able to solve all of these using what I have taught you. Right now, some of these are similar to ones we've done, but some of these combine the knowledge of what we learned about with the trigonometric and exponential functions with the product rule, chain rule, quotient rule, sum rule, everything else I taught you. Right? So you're going to have to use those two pieces of knowledge in conjunction. I haven't shown you how to do that, but you should be fine. Right? It's not something too complicated. We just need to use the same thing. What's the derivative? What's the function? Same thing. Right? So we've got some. These ones are, I won't call them simple. They're actually pretty difficult, but you should be fine. These ones are extra difficult, right? Just because it's kind of difficult to get your head around it, but let me give you a hint for these ones, okay? So e to the power x is just another function, right? So I can write, imagine I write e to the power x as x of x, just abbreviating it as another function. This just becomes e to the power 9x becomes x of 9x, right? So my point is this is a composite function. It may seem kind of different, but it is just a composite function. It is e to the power x is the outer function and 9x is the inner function. So in both of these, you should use the chain rule. Now, how to use the chain rule, I'll leave that up to you. I'm not going to do the problem for you, but just a hint. But so as always, try, I encourage everyone to do these. I encourage everyone to try these. Even if you're not able to do them, not a big deal. But I still encourage everyone to try these. Okay. That being said, that is the end of this lecture. Hopefully you found it interesting. Hopefully you learned something. As I said, as long as you learned something, I have succeeded at my job as a professor. Hopefully you enjoyed it as well. I've tried to make these lectures as enjoyable as possible while still sticking to the content. So yeah, hopefully you've taken something of value away from this lecture. Thank you for attending it. And I will see you next week with the hopefully new and interesting topic for lecture.